Well, here we have today the BOE BOT robot kit. I've been thinking about getting one of these for a long time after seeing a friend have one and how nice of a robot it actually makes. Um, Unfortunately, I'm not really interested in the educational. BOE stands for Board of Education bot, and I guess students that take college classes will buy this kit for about 200 bucks and take the university class and then either go on into robotics or computer science, or they will decide it's not for them and they wind up selling the kit. Now, the kit, like I said, is about 200 bucks. I found this online on eBay, or maybe it was Craigslist. I have a program that does a universal search, a nationwide search on Craigslist. And I think I got this for about 40 bucks, which was a very good deal. It was brand new. Um, Only been used for by this one student for a university class, and they decided not to move in or move on to doing a robotic education, so they sold it. Now these kits are different prices. They range from, I've seen it as cheap as 35, 40 bucks all the way up to $140. There's other modules that come with it, like this some sort of feeler gauge here, whiskers they call it. This kit didn't have any of that. It came totally complete. I have the whole box. There's even some of the LEDs and sensors that haven't even been opened yet. It uses a different coding environment or coding program to upload code to the PC board. I'm not interested in learning that code, or actually, like I said, even using this board. It's kind of limited and the parts are pretty expensive. If you want other additions or add-ons, the Arduino is definitely a better way to go, or maybe even the Raspberry Pi if you want to go that route. But the Arduino is ideal for this. And so I've been looking for a while and I finally bought one. And so let me show you what I actually bought. This is the kit here, and this is the actual bot that came with it. Like I said, it comes with a motherboard. It came with 2 servos and a battery pack. It came with an extra servo, which is kind of nice. These are continuous servos for the wheels. It has the metal frame. This is a standard servo. So, and then all the wires and connections to make it work. The only problem is, and I'm going to use my Arduino Mega to control it because I'm using the Uno for a different project, is that the Uno doesn't really screw into the base. And so that's kind of a problem there. Parallax, which is the company that makes this, does make an additional little module that looks like this. And basically, the holes here match up on the holes on the top of the computer of the robot of the Bobot, and then the Arduino mounts underneath this board, and the pins come through here, and you can access them and then do what you want with them. So actually, the module, the Arduino, would be underneath like this, and then the pinouts would come up through the top. Well, as you can see, this is $40. I don't want to put another $40 into it. This is the top view of the little board. It's ideal. If I could find one used for 5 or 10 bucks, I'd definitely pick it up. But for 40, I don't want to sink that much money into it. But this is a nice little clean solution. So depending on how much I actually put into this project, I may wind up buying it anyway just to make it cleaner. But for right now, what I've decided, I'll show you what I've decided to do, is I take this off and unscrew this, and I take off the breadboard and I turn this upside down and just put the screws back in here and use the board upside down. And I'm using some Velcro here to hold the breadboard and to hold the Mega. And for the most part, while I'm doing prototyping, this will be fine. And I think for right now, it's on there pretty good enough. I also had a servo module here that is it's a clamp that holds a servo. I mounted that to the front of the BOBot because I had the kit included an extra one. So I will put a ultrasonic ping module on there and have it rotate around and use the small micro breadboard for connecting things. So for right now, I think this will work well. This actually plugs in here. These are the servo connections here, and I need to connect these to the breadboard and use it that way. So that being said, for 40 bucks, you get I got 3 servos and some nice wheels and a really nice metal robotic car. So I wouldn't spend much more than 40 because, like I said, I'm not going to use the actual PC board that controls the car or the software or the other little kits. So for me, 40 bucks is pretty much the limit. If you can find one, this is in brand new shape. If you can find one, my friend picked one up for $5 at a local college. So if you get lucky like that, great. And this robot car kit is really a nice one. It's very durable. It's expandable. It has all these little places where you can mount other components. I highly recommend trying to get one. The servos drive the wheels very nicely, and I was really impressed with my friends. So that's what compelled me to get one. So given that, this is the start, and I'm going to start adding modules and increasing the capability of this, and I will document it as I go along. Diagram. It has a ping module, a Bluetooth module, and an MPU6050 plus 3 servos. I have a separate C battery pack for the servos and 9-volt for the Mega. Here I have the BOBot car doing a series of 5 rights and 5 lefts. Each turn is calculated using the MPU6050 chip's yaw feature. Even though the chip is a 6 degrees of freedom, it has pitch and roll and yaw in both directions. I only use the yaw for left and right. And then, since that's the case, the yaw counts clockwise 0 to 179, and then counterclockwise from 0 to negative 179. So you have to account for this difference in numbering when you calculate your left and right turns. In this case, it works very well. So here we have the hyperterminal view of a right and left turning only test that I did. I wanted to show how the car turns right using the guidance system that's provided by the MPU value, and how it goes from 0 to 90 to 179, back to 90, then back to 0. And here it's just doing a bunch of rights, and about 5 of them, then a bunch of lefts, again about 5 of them, then rights again. And what's interesting to note here is the MPU value counting towards the heading value, and then once it meets that heading value within plus or minus 10 counts, it stops and then does the next turn. In this case, it'll be multiple rights, multiple lefts. Because servos don't track evenly, I've written code to slightly adjust left or right the BOBot car's direction so that the MPU value and the heading stay equal. I have the hyperterminal capture from the Bluetooth of the BOBot car doing a micro adjust left and right, and eventually it does a right turn here. The BOBOT car driving on the floor, and I test the left, right, forward, and reverse capabilities of it. I'm just using a simple paper plate to kind of act as a barrier so that the ping comes back and can work correctly with the received data. But basically it's pretty straightforward. Just wanted to kind of show how it moves about and how quickly it turns. So this sketch that controls the BOBOT car that I purchased was fairly complex, and I have quite a few notes. So what I want to do is I want to start off by giving the notes that I used right here to configure the car and do some analysis and some background education for myself. And I also want to give some verbal notes that I took while making this project. Often in the projects I do, I write down notes and kind of sideline information. And I want to give kind of a background to this this project because it was pretty complex. Basically what we have is a Arduino Mega, and it's controlling 3 servos. There's a right wheel, a left wheel, and then a center ping servo for judging distance to objects. In addition to that, there is an MP3, I'm not MP3, but MPU, which stands for Motion Processing Unit 6050. It has 6 degrees of freedom. It does a pitch up and down. It does a roll left over right, and then it also does a yaw, turning left and turning right. So those are the 6 degrees. It's a gyroscopic accelerometer. It does quite a bit, and it wasn't very expensive. I got it at Banggood. It was maybe $5 or $6. And I think they're basically used in segways to keep them upright, or if you're doing a 2-wheeled stand-up robot, you would use it also there, which I might make in the future. Overall, it was a very cool project. What I wanted to do was I wanted to just use the yaw portion of the sensor, the left-right, kind of like a compass. But I didn't really want to do a compass. I don't really need to know true north or true east or west or south. Every time you turn on the MPU6050, it starts out at heading 0. And so this BOBOT is basically a line following robot. However, there's no line. It uses the heading signal from the MPU6050 to keep it on track. And if it's going forward, it's initially set to 0, and it will try to keep the MPU6050 heading at 0. I do micro adjustments left and right because servos are not as precise as they could be, and so it bumps it back into line. When it goes to do a turn left or right, I set the heading to 90 and I turn until the MPU6050 reads 90 and matches up with the heading. So I'm always constantly matching the heading and the MPU value, which is the get value I use to find out what angle I'm aiming at, so that they match up. Now, something's interesting. The MPU6050, if you go clockwise, goes from 0 to 179. If you go counterclockwise, it goes from 0 to negative 179. So you have to account for that. And what I do is I convert everything to an absolute positive. So it's if it goes right, it's 0 through 179. If it goes counterclockwise, it's 0 through 179. And it basically, if it continues to go in a right direction, it would go from 0 to 90 to 179, back to 90, back to 0. And the reverse is the same. So you got to kind of keep the direction that you're going, keeping tabs on that, and all the different angles. So it was a tricky calculations to do. But basically, I'm using the MPU 6050 as a guidance system, and basically, I took or used some of the code or most of the code that was produced by a gentleman by the last name Berg under a program called Processing Plane Code. I have it up here in the notes. You can look for it and kind of look at it yourself. But it gave you the yaw, pitch, and roll. I discounted 2/3 of it. All I wanted was the yaw value. And what it does is it would take values from the Arduino and then graphically using the processing program graph it like a plane in three-dimensional space. So as you rotated the chip, you would see the plane move in the same correlation. And so I initially wanted to be able to take the information from the BOE BOT via Bluetooth, and that's another bit of hardware that's on this car, is I also communicate via Bluetooth. I wanted to capture that Bluetooth information and graphic three-dimensionally on the screen. However, I couldn't get an answer from the processing folks to be able to convert that data to three-dimensional graphic image without shutting off the Bluetooth connection. So I never got that to really work in that fashion, which maybe in the future I will try. So we have all those devices, and then so the servos require a lot of power. I kept running out of the AA batteries that worked underneath the chassis, the 4 of them that came with it. I kept having to replace those, so I got a little tired of that, and I upgraded to 4 C batteries, and then I used a 9-volt battery just to control the Arduino Mega, and that seemed to be the best. However, it's not the prettiest. The car doesn't look the greatest, but it's pretty solid, and it worked pretty well. So let's see, what other notes do I have here? One thing that was very difficult was having, I had difficulty with the wheel speed. Each wheel of the servo, one on the right, was, as you're looking at, because you can either look at it from the back or from the front, but as you're looking at it from the front, in this case, the right wheel actually would run, I believe, backwards, and then the left wheel would run forwards when you're going forward. Stop was not actually 1500, but it was actually 1492 for both wheels. That's where it actually stopped the wheels from moving. And then reverse, as you're looking at, the left wheel went backwards at 2300, and the right wheel went backwards at 11. And the reverse is the same for forward. The right wheel went forward at 2300, and the left wheel went forward at 1100. A good forward speed that seemed to keep the wheels as even as possible so that it tracked in a fairly straight line. The right wheel speed I found to be 1700. I guess these are in microseconds. And the left speed was 1200. And that seemed to work pretty well for me with the servos I had. Your servos may also change. So one thing I also want to do, since I upgraded the power supply, you got to keep the power supply definitely in the middle of the car. I tried hanging the power supply off the back, and it would lift up the front, and it didn't really steer very well. One downfall of the MPU 6050, on occasion, randomly, it will return a very large heading, or it will lock up, and so you got to kind of keep on top of that. To make sure you're constantly polling it, or you don't have too long of a delay, because that MPU 6050 will shut down or stop or give you a bogus number, and then your numbers get off. Now, I didn't do any error correction or detection on that. I could have probably polled it twice and taken, or 3 times, and taken the 2 numbers that were the same and used that. I didn't do that, but if you're doing something that's much more critical, you might want to try doing that. Let's see, what else? I wanted to I had to slow down the MPU 6050 from 115K baud down to 96 baud. That also caused some problems. So when you start slowing it down, it starts to hang and give you bugs. So I kind of tried to minimize the code to get it to process as quickly as possible. So I did mention that the heading starts at 0. You have to allow some time for the servos to kind of stabilize, and also you have to allow the MPU6050 to stabilize. I only allow it to stabilize a little bit less than 15 seconds, but it could take as long as 40 seconds. That's just something to keep in mind. There was some, let's see, other than that, I think that's probably all the notes that I had on the side. So let's look at the code here and go into that. So these are the notes I used for searching for information. Here's the name of the sketch right here. You can find at CodeBender under user fish. I also have other YouTube videos if you search Scottmon on YouTube. Here's some information that came with some code. I'm leaving it in there. I didn't actually use it. Here are my notes on the servo 1 and servo 2, how they, the forward and backward direction for the wheels. Here are all the libraries I used. And up above, you can download whatever you need, like this one here up above. I always put in pragma once because that stops multiple openings of the same .h files. That seems to help. And here I configure the MPU6050. This is some information that was with Berg's code, so I left it. I created my own MPU value, here's some negative. If the value is negative, I need that information, because when I count to the counterclockwise, I need to convert, but remember that it was negative so I know which way to turn. This YPR is yaw, pitch, and roll. This is part of Berg's code, so I left it. Again, same with this. Here's heading. Basically, the MPU value and the heading, you're always trying to match those up, and you only change the heading in very key subroutines or functions. You don't want it changing all over the map, because pretty soon you'll lose track of where your heading is. I set the speed to forward. I initialize the word stop to this number here. This is for doing some mathematics down below, which I will describe. And then here's the heading counter for turning. This dump data ready, I did not generate. It's basically part of Berg's code for the MPU6050, and you need his code. It's definitely the way to go. Here I configure the ping module, very standard, trigger pin on 9, echo pin on 8, and then a max distance of 200. I think it goes as high as 4, but I just did 2. Here I configure the servos, left wheel, right wheel, then center ping. The distances, so that, and then a limit distance of 10. So if I get within 10 centimeters, I guess it is here in this case, it stops and starts to calculate which direction to go. Here I set up the sonar for new ping setup for pins and maximum distance, and the actual setup portion of the code right here. Let's see. Some of this is Excel, MPU, Excel, offset is part of the MPU code that you need. These are the numbers that came preset with it. I used a calibration program, which I will include. It's up in the notes up above, that you can download, and it will give you a little bit better numbers here so that you get truer, more accurate results with your particular MPU6050, and I did adjust them slightly. Here's an interrupt you have to have. You try to take the interrupt out and it stops working, so you got to leave it in. Here I attach the wheels and the center ping to the servos. I just stayed here. I have setting the servo in the center to the center, and stop the wheels so that we're ready. I give it a few seconds because I need to set it up and push the reset and connect a bunch of stuff, so it takes a little bit of time. Plus, you want a little bit of time for the MPU6050 to initialize and the servos to initialize. The heading set to 0, MPU value is set to 0. so that you're starting off in a forward direction. And then here's the loop, and this is the main portion of the program, obviously. We come into the center ping. We initialize looking straight ahead using the center servo. I display the wheel information on the screen. I'm using that with Bluetooth and the serial monitor, and then I go forward. And I'll show you the code, the functions down below when we get there. Next, I get the MPU value. Check to see if we're varying left or right, because you want to go in a straight value. And like I said, servos are slightly different, and over a long distance, they will start to deviate left or right. And you want to make sure you're on a straight heading. I take the absolute value of that value, whether it's negative counterclockwise or positive clockwise, and if it's different, not equal to 0 heading, we check the heading, and under check heading, it modifies, it does an adjust right or adjust left to get the heading and value, MPU value, to match up again. I display that information. Otherwise, if they are the same, we check the center distance, see if there's an obstacle at our limit. This is standard code I had in my other robotic car code, but if the distance is greater than this, we go forward, we check the center again, else we stop the left and right wheel, we give it a few seconds to stop, we get the distance right, we get the distance left. If right is greater than left and right is greater than limit distance, we go ahead and we center it and turn right. We center the ping module and then turn right. Else, if left is greater than the right distance and left is greater than limit distance, let's turn left. Center the ping module, turn left. Else, we reverse. That means there's something on the left and something on the right. We reverse. Basically, after all that, we get the next MPU value, and the whole process starts over, and that's the end of the loop. And so we're constantly getting this MPU value to make sure that we're heading, whatever direction we're heading, we're always heading on that line, that guided line provided by the MPU6050. So here's the code for the right. I show, it makes a right turn. You got to align it with the heading. It cycles degrees of the MPU. MPU never has 180 or 360 degrees. That's key to know. So you got to be able to cycle that information, but not get to those numbers. Must take into account if it turned left prior to a right turn, or if it turned right. Must take into account if it turned left prior to a right turn, or if it turned right prior to a right turn. So is it going in the right direction, or is it going left, right, and that's, you got to handle those a little bit different. So this gives me a little example I just wanted to remember, and that's how I decide whether it's a 0, 90, 179, 90, or 0 as a remainder. I check the division, and I check the heading, and I check the remainder in the code down here, and that allows me to calculate this next number. So in a right turn, I print right, and I said heading counter equals heading counter plus 90. So if I was doing 0, I'm now doing a 90 degree for a right turn. And I take the remainder, and I take the division, and then I make a comparison, and if it's not 0, then the remainder is 179. If it is 0, then the remainder equals 0, and then I set the heading to the remainder, because if you notice, the remainder is really all the values I want. After that, I get the MPU value, I display the wheel information, and then while the MPU value is not equal to heading, because we're starting to turn now, we're going from 0 to 90 right here. And it might be from 90 to 180 or 179. So it depends on what, if you're going right. And then what I do is right wheel, right position, and the position is from stop. I keep adding, which is 1492. I add 15 degrees or units or counts, and I turn the right wheel, and then I turn the left wheel the same amount because it's going in reverse. And I give it a little bit of time to do that, and then I get the value to see, have we gotten to these two numbers being equal. And in fact, in this case, I actually give it a little bit of a buffer of 10 clicks or 10 counts either side. So it doesn't have to be exactly 90, it could be 95 or 96, so that because the wheels don't turn as precise as I would like, and I also didn't spend the extra time to get it to land precisely. It's really difficult. You could just move slower, you know, until it actually lands on it. And then you get a much more accurate 90-degree turn. So it was what it was. It worked fine for me. Basically, let's see, where do we go from here? So after we finish here, at one time I had for testing, I had a bailout to get out of a loop, but it looks like I don't need that anymore, so I'll get rid of that. So once these two numbers meet, oh whoops, I see, there's the bailout. Edit. Yes, I'm sorry, I need to point out something here. We stay in this loop and we keep doing this, but once this is true, we go to bailout, and otherwise it'll just keep testing and testing and testing. It'll just cycle over and over and over. I did not code this as well as I should have. I could not seem to figure out how this while loop could keep going, and when I meet a certain buffered area or boundary area between of the heading, to end this while loop. So even a do until, or maybe a do until might have worked. Maybe I could have just done do. I don't know. I never really got this to work so well, so I used a go to, which is not too good. But so then you go to bailout once this is true, and then you stop, and you set the right wheel and left wheel to a stop. You give it a little bit of time, and then once it's stopped, you start moving forward again. And that's the right turn. The left turn is exactly the same, except you deduct 90 degrees. And other than that, it does exactly the same thing all the way down. Here you keep doing this loop until MPU value, while MPU value doesn't equal the heading. You keep doing this. So you keep going, going, going. And then eventually the MPU value will land in between heading minus 10 and heading plus 10, in which case you blow out of it, go to bailout again. And again, like I said, I'd like to code that a little bit better. You stop, set the wheel speed, wait for it, then go forward, and that's the end of the left. So now that we're going left, let me go down here to the forward, which is way down here. Forward is you set the right wheel speed that, left wheel speed that, and you just go ahead and do it, and that drives you forward. Reverse. These are the backup values for the wheels. The reverse values, you set them, you delay a little bit of time to back up. This is the amount of time you back up, and then you stop. So that's basically the reverse. So that those are all the different directions. Let me go back down here. Now, getting the MPU value. What exactly does that do? This calculate the MPU yaw value. This value is used as a straight line to follow the value is established when the unit is first turned on. So while there isn't an interrupt, and I'm not familiar with this code so much, I reduced it down quite a bit because a lot of it I didn't need, but basically you need this. You're setting up some sort of buffer and packet size, and then you got to reset it. Here, as the buffer gets filled up, you're putting the value. This is so that it can actually be kind of sent to the processing program, which I don't even use. I try to remove what I could, and basically I set the MPU value right. Well, I set it here, and then I check to see if it's negative, in which case I set it true if it is, and then I take the absolute value, not conserve, it's convert, that spell check, convert to positive. So this is his code, Berg's code. I just kind of reduced it down because it worked so well. After you get the value, you want to check your heading. And if it was negative, then we adjust the bot right. Else we can adjust it left. And this is for keeping it on the heading. Check to see if the BOBOT car is veering off the MPU6050 heading value, i.e. 0, 90, 180 degrees. Adjust from looking from rear of the bot car. This is looking from the back of the car. So when you adjust right, it's actually the left wheel that you're adjusting. So you're going counterclockwise. Thus, if it's a negative, you adjust right. Else, if it's positive, you adjust left. And again, you're looking at the right wheel. So I probably could have reversed this or done this a little different, but it was just easier to see it in my mind's eye. Instead of looking at the front of the car, I'm actually looking at the back of the car, having it adjust right or left. And then we set the value negative back to false, and that's the only place we set it to false. So other than the setting at the top where it's initialized initially. So that's the check heading. And so we're constantly checking the heading, comparing the MPU value to see that we're online with the heading. So the adjust left and the adjust right are very similar. If the BOBOT car starts to drift right, adjust the direction back towards left. This adjustment is viewed from behind the car. Here I print out a little message so I know what's going on. Here I have a value. In this case, on the left, I add an offset, and I keep deducting that offset to slow down the wheel or speed up the wheel. Here it speeds up the left wheel so that it starts to turn left more quickly, and I slow down the right wheel so it starts to pivot. And then once it gets to this value, this is the minimum value I want to get. I just set it back equal to that. I don't want to exceed the maximum speed of 1100 because it doesn't really do any good. And I didn't want the wheel speeds to start getting crazy. Here, 1500 is darn near stop. And so once it gets past that, I want it to keep moving a little bit. I go ahead and activate the servos, and then I display the wheel information. The adjust right is exactly the same, except I handled it a little bit different in the fact that here's the value. I initially started using that, but then I thought for the right, it was easier just to set actual values for turning, and that worked the best for me. I tried these different values, and this one was the best. So this really is not necessary anymore. I could actually take that out. Then once it's turned to the right and the heading up above says they're equal, then I stop calling adjust right. And I want to display the wheel information to the console so that the Bluetooth or the serial monitor will tell me what's going on. So the next function is get distance right. This is real simple. You just set to 10, look right using the servo, give it a second to do that, get the distance, return that value. Same with get distance left, turn it to the left, 170, give it some time, get the distance, give it some time to get that, return the value. And the center is at 90. Here it was, I put it to 500 to get it so that I can speed up the code as much as possible. These delays you probably could reduce a little bit in order to speed up the code, but I didn't need to. So here's a delay. If the value is 0, I set the value to 200 because that's infinite. We don't have a distance of 0. Sometimes 0 comes back if it goes off to infinity. So I just set it to 200, our max value, and then I return that value. Forward I already told you about. Reverse I told you about. Here's get distance. Get distance basically is a standard ping code. A lot of folks use it. It's readily available. I've used it in other ping projects. So you do a sonar ping, you calculate the ping value. If it's 0, I set it to 200, and then I return that value. Else I return the actual ping value. How close is it to something? Lastly, here's display wheel information. I set the display what the right is at, the left is at, the MPU value is at, and the heading. And that's basically it. So that, in a nutshell, is the code. I hope this is helpful. It's not the most beautiful coding I've done, and the project was pretty difficult actually with all the functionality. I really wanted to be able to run the car autonomously, let it just run, and have it graph the information, the car turning left and right in the processing program, and see that in real time. And I'm still trying to work on that. But unfortunately, I'm not getting a whole lot of help from the processing folks so far, and I can't get the processing program to run the same time I have Bluetooth running on the serial port. So yeah, that's to be determined in the future. I hope you enjoy this sketch and this program. Please share it. Please give me the thumbs up if you like it. Please, I would also be nice if you want to subscribe to my other videos. I'll keep putting some out there, and I hope this helps you.